Alright, now we're going to be doing problem number 2 of homework number 5. Now, what is provided to us in problem number 2 is this function right here. So we have a joint function, a joint density function, which is defined as 1 over some unknown constant a times x squared y. What we're given is the parameters whereby the term x is going to be greater than or equal to 1, and we're given that y is going to be between 1 over x, that's going to be the lower limit, and the upper limit is going to be x. This problem has 4 parts, so let's get started. The first part is this asks us to draw the non-zero region for this for the density function defined right here, which we do on our xy plane right here. All right, we're basically going to be using these parameters right here to define things. So first and foremost, if we define x greater than or equal to 0, so basically we're going to be ignoring everything to the left of this line, and we're only going to be looking at things to the right. On the y-axis, the lower limit is defined as 1 over x. Now, 1 over x is defined as an asymptotic function. It goes right here. It's infinite toward the y-axis. Then as it goes toward the x-axis, it plateaus, going toward y equals 0. All right. And obviously, we have the linear function defined as our upper limit of x right here. All right. So if we're just looking at everything to the right of this line, we see that these two functions meet right here, right where x is equal to 1 and y is equal to 1. All right, and since this is our lower limit and our upper limit, we're going to be looking at the area, non-zero region above this curve and below this line. So we're going to be basically looking where all these squiggles are right here. I mean, it extends out this way, but that's going to be our non-zero region for our joint function. So that's part 1. Now, part 2 is asks us to find a, basically, so that this ends up being a valid joint density function. So how do we do that? Well, what do we mean by having a valid joint density function? It means that basically the corresponding distribution function, the big F of xy, is going to be, if we integrate it over negative infinity to positive infinity, it's going to be equal to 1. So in this, I mean, it's going to be the same thing we've done before in other homeworks, but we actually are doing now a double integration. So I write it down right here. Our joint big F right here, we're going to be integrating twice over right here. We're going to be integrating first over y and then over x. Now, over y, as we explained right here, we have limits, lower limit, 1 over x. Okay, our y is defined in terms of x right here. All right, upper limit, x. And then our outer integral, defined in terms of x right here, we're going to be integrating from 1 to infinity. All right, and what we expect is that when we do that, we're going to have a function equal to 1. So, using that, we basically can find the double integral of this term, equate it to 1, and solve for a. And that's what we do right here. So we substitute our function right here. Okay, we can take, because this integration deals with delta y first and foremost, we can take out constants or our x variable, which we do right here. So this ends up being 1 over y. All right, the integral of 1 over y is basically our natural log, which we evaluate from its upper limit to lower limit right here. If we go right here, that equates to this right here, our natural log of x minus natural log of 1 over x right here. If we substitute, subtraction, is this going to be natural log of x over 1 over x, which is basically the natural log of x squared. All right, so that's what this function is. We substitute that right in here. All right. Let's see. Now we have this 2 right here. How do we do that? Oh, of course. So what we ended up doing is, because we had natural log of x squared, because of our rule of natural log, we can actually bring out the exponential function and bring it out and make it a constant. So that's what we did here. So what we did was make this natural log of x right here, and we brought out the 2. We made it a constant right there. Okay? So now we can integrate across our outer integral. All right, we can take out the constant terms, okay, which in this case is going to be 2 over a. And we're going to be integrating the natural log of x over x squared dx, okay? And like I said, lower limit 1, upper limit infinity. And basically this term right here can be, we do a little rearrangement. Let's bring this up here, -2. All right. And then we use the actual formula for integration. We work out the arithmetic right here, substituting in. All right. It's just basic arithmetic we're going through. Forgive me if I'm going a little fast. What this works out to be ultimately, this at infinity isn't fine because 1 over infinity is going to cancel all this out. So we're just going to be looking at 1. So it's going to be 1 substituted in there. All right. We're going to add because we're subtracting, we add a negative term right there. Natural log of 1 is 0, so this canceled out. This is going to end up being 2 over a, which as we set up here is equal to 1. And if we just do this, we see how a is equal to 2. So our final answer is going to show that our joint density function, little fxy, is going to be equal to 1 over 2x squared y, whereby x is greater than 1, and our y is defined as we described earlier. So that's part 2 of our problem. Now, part 3 is find and draw the marginal probabilities, basically little f in terms of x, little f in terms of y. All right? So how do we do this? Well, basically given the theorems that we have in the book, or on the notes, little f of x is basically we take the joint density function from -infinity to positive infinity over y. So we do a single integration, but not in terms of x, in terms of y. And we do the same thing for little f of y. We go from -infinity to positive infinity of our joint density function in terms of x. So that's what we need to evaluate to find our marginal probabilities. So we basically plug and chug at this point. So we take our function up here, bring it down. So we're going to do little f of x. In terms of dy, we can bring out the 1 over 2x squared. So it's, again, 1 over y. Again, we mentioned that up here, that's equal to the natural log, which in this case, again, we're going to be evaluating from our same lower and upper limits. And that breaks down basically to be, because we did the arithmetic up here, but basically, as we said before, this is going to be, this is going to work out like that right there. Basically, we got rid of the 2 because remember, this comes out to be an x squared. We bring out the 2. Works out fine. So our final term for little f of x is going to be equal to natural log of x over x squared, whereby we define x between 1 up through infinity. Now, when we evaluate little f of y in that same way in terms of x, we actually have to divide our problem up a little bit. All right? Because the way, if we look over here, the way as we described, we're talking in terms of x, but we actually have our function broken up into 2 parts based on this line here and this line here. Okay? So when we actually write this out, all right, especially when we write out the actual the limits in terms of y, all right, we're going to have to actually break this up and look at the limits as defined, whereby it's this term right here. We have it written as y equal to 1 over x. We can see how we could easily rearrange that into x equals 1 over y. This, y is equal to x is equal to y, and so on. All right, so when we actually break up our problem, first we do from y 0 to 1, which is defined by this function right here. All right, we take our big F that we had earlier. We integrate it over dx right here. We have our limits, all right, which we have the lower limit. Upper limit is going to be infinity. When we work things out right here, we can see how we can actually do that. We brought out constant terms because we're working in terms of x right here. So we brought out 1 over 2y. That just makes this 1 over x squared, or 1 to the negative 2. We work it out right here. We evaluate it over our limits. I mean, infinity is this is going to be 0, 1 over y. We substitute in. That ends up being y over 2y, which is 1/2. So basically this term is defined where y is between 0 and 1. Our function is defined at, our little f of y is defined as 1/2. Now, between 1 and infinity for y, all right, we actually evaluate things by the other limit. You know, x of y is the lower limit, and then we go to infinity. And what ends up here and being here, we do similar things right there. All right, our function is going to be almost exactly the same, except the limits are going to be different. Again, nothing comes out of this because it blows up. Lower term, we substitute in y for this. All right, when we evaluate it, we get 1 over 2y squared. So, our little f of y is going to be defined in pieces. Basically, for y between 0 and 1, it's defined as a straight line at 1/2. Between y from 1 to infinity is defined by this term right here, which is 1/2 times y squared. Otherwise, it's equal to 0. And now we can actually see the drawings for these terms right here. All right. If we go back and look at our little f of x right here, remember we defined it starting at 1 and going to infinity on the x-axis. So we start here. If you look, I just a little exaggerate. It's more of a subtle curve that then starts plateauing, but it crosses the x-axis right here. And then this term right here, we can see how it corresponds between, on the y-axis from 0 to 1, we have a straight line. And then this term is an asymptote that plateaus slowly toward the y-axis. And that's our drawings. The final part of the problem asks us to evaluate whether our marginal probability functions are valid. The way we do that is just basically take what the functions that we calculate here are our little f of y, our little f of x, and we integrate. All right, we integrate along their limits to get the big F of y, and what we should get is 1. And if we get 1, we validate the actual functions. So if we take, this is the function I just described, we take that from 1 to infinity. If we break that down, this is the equation that corresponds to the integral of this equation right here. All right, this is just the basic arithmetic. All right. This breaks down to negative log of x minus 1 over x from infinity to 1. At infinity, it blows up right here, so we get 1 right here. Subtract it, so we got to break out the actual negative term. This ends up being 0 plus 1, 1. So we verified that our little f of x is correct. So now, what about our little f of y? Again, we're going to be looking at our function here. As we said, we broke it up into 2 parts, from 0 to 1 and then 1 to infinity. 0 to 1, we can see here what its integration is going to be. It's 1 times 1/2. So we just plug in 1/2 right there. This corresponds to that. The important part is working out this problem right here, which corresponds to this equation we did right up here. All right. Which we break down, we bring out the 1/2. We can see how we actually evaluated the integral. We're going to do it from infinity to 1. Infinity blows up again. 1 we plug in. It's going to be this 1/2 plus 1/2. This equates to 1. And the whole thing, 1/2 plus 1/2 is equal to 1. So that's it. We evaluated that our little f of y is indeed a valid density function. So that's the end of problem number 2.